Hello, ma'am. Hello, everyone. For the lecture 3, electricity, I'm going to explain um, the problem set. So, for problem set number 1, example 5.1, the force on the electron in hydrogen. So, the hydrogen atom consists of a single proton and single electron. The proton has a charge of positive E and the electron has negative E. In the ground state of the atom, the electron orbits the proton at most probable distance of 5.29 times 10 raised to negative 11 meter. Calculate the electric force on the electron due to the proton. So in this problem are given so um, our two charges and the distance between them. So the two charges first is the charge 1, which is positive E, is equals to positive 1.602 times 10 raised to negative 19 coulombs, and the charge 2 is equals to negative E is equals to negative 1.602 times 10 raised to negative 19 coulombs, and their distance, the distance between them is equals to 5.29 times 10 raised to negative 11 meter. So in this problem, we're going to calculate the force on the electron due to the proton. So um, we're going to use the Coulomb's law in this problem. So the magnitude of the force on the electron is force is equals to 1 over 4 times pi times the um, E sub O, or the epsilon sub O, times the absolute value of E squared divided by R squared. So substitute the value. So 1 is equals to 4 times pi times the value of the epsilon sub 0 is equals to 8 times 85 times 10 raised to negative 12 coulombs squared over Newton times meter squared. So times the absolute value of the electron. So 1.602 times 10 raised to negative 19 coulombs squared divided by the r, the distance between them, 5.29 times 10 raised to negative 11 meters squared. So the answer would be 0.00000008246, or 8.25 times 10 raised to negative 8 Newton. So as for the direction, since the charge on the two particles are opposite, the force is attractive. The force on the electron point radically directly towards the proton. Everywhere in the electron orbit, the force is thus expressed as force is equals to 8.25 times 10 raised to negative n Newton in r vector, or r vector is the vector displacement from the charge 1 and 2. Problem set number 2, example 5.2, the net force from two sources charges. So three different small charge objects are shown in figure 5.17. The charges charge 1 and charge 3 are fixed in place. Charge 2 is free to move. So given charge 1 is equals to 2e, charge 2 is equals to negative 3, and charge 3 is equals to negative 5e, and that distance is equals to 2.0 times 10 raised to negative 7 meter. What is the net force on the middle charge, charge 2? So required, we're going to find the force of the charge 2. So solution, we're going to use the again the Coulomb's law. So we have two sources charges, which is the q1 or the charge 1 and the charge 3. A test charge, which is the q2, and distance, which is r21 and r23, and we are asked to find the force. This calls for Coulomb's law and superposition of forces. So there are two forces. um, Net force is equals to the net force 21 plus net force 23 is equals to 1 divided by the 4 times pi times the epsilon sub 0 times the negative um, the net electric charge of the two objects, or the q1 and q2, over r sub 21 squared in j vector plus negative Q2 Q3 um, over R sub 23 squared in I vector. So we can't add the forces directly because they don't point in the same direction. So the net force sub 12 point only in the negative x direction, while the net force 13 point only in the positive y direction. The net force is obtained from applying the Pythagorean theorem to its x and y components. So we're going to use the Pythagorean theorem. So they um, f squared is equals to f sub y f sub x squared plus um f sub y squared. So they square both sides. So the final um the final um net force is obtained, which is net force equals to square root of f sub x squared plus f sub y squared, where fx is equals to negative f23 is equals to negative 1 over 4 times pi times epsilon sub 0 times q2 q3 over r sub 23 squared. So substitute the value. We know that 1 we know that the 1 over 4 times pi times epsilon sub 0 is equals to 8.99 times 10 raised to negative times to 9 Newton times meter squared over column squared. So times to the net electric charge of the two objects is 4 times 806 times 10 raised to negative 19 coulombs times 8.01 times 10 raised to negative 19 coulombs divided by 4 times 10 raised to negative 7 meters squared. So the answer would be negative 2.16 times 10 raised to negative 14 Newton, and Fy is equals to F21 positive 21 is equals to 1 over 4 times pi epsilon sub 0 q2 q1 over r sub 21 squared. So again 1 over 4 times pi times epsilon sub 0 is equals to 8.99 times 10 raised to 9 Newton per Newton times meter squared per coulomb squared. So q2 q1 is equals to 4, same from the previous solution, 4.806 times 10 raised to negative 19 coulombs times 3.204 times 10 raised to negative 19 coulombs divided by 2 times 10 raised to negative 7 meters squared. So the answer would be 3.46 times 10 raised to negative 14 Newton. We find that f is equals to square root of f sub x squared plus f sub y squared is equals to 4.08 times 10 raised to negative 14 Newton at an angle of theta is equals to tan raised to negative 1 fy over fx equals to tan raised to negative 1 times 3.46 times 10 raised to negative 14 Newton divided by negative 2.16 times 10 raised to negative 14 Newton is equals to negative 58 degrees. So that is 58 degrees above the negative x axis as shown in the diagram. Problem set 3, example 7.4, calculating energy. You have a 12 volts motorcycle battery that can move 5,000 coulombs of charge, and a 12 volts car battery that can move 60,000 coulombs of charge. How much energy does each deliver? So based on the given problem, for motorcycle have 5,000 coulombs of charge and 12 volts, and for car it has 60,000 coulombs charge and also 12 volts. So in this problem we're going to find the potential energy of the motorcycle and the potential energy of the car. So solution for motorcycle, again for motorcycle we have 5,000 coulombs and 12 volts. So the total energy delivered by the motorcycle battery is the potential. We're going to multiply the charge and the volts in order to get the potential energy of the motorcycle. So um, 5,000 coulombs times 12 volts, or volts can become joule per coulomb. So 5,000 times 12 joule per coulomb is equals to 60,000, or um, 6 times 10 raised to 4 joule. And for car has 60,000 coulombs of charge and 12 volts also. So the total energy delivered by car battery is 60,000 coulombs times 12 volts is equals to 720, or 7.20 times 10 raised to 5 joule. Problem set 4. Example 7.5. How many electrons move through a headlight each second? So, when a 12 volts car battery powers a single 30-watt headlight, how many electrons pass through it each second? So, based on the given problem, we have the 12 volts and um, the potential energy 30 watts, and we're going to find the number of electrons, or the how many electrons pass through in each second. So solution: to find the charge move, we solve the equation. Potential energy is equal to charge times the volts. So by simple manipulation of this formula, we get the charge is equals to um, potential energy divided by the volts. So entering the value for potential energy and volts, we get charge is equals to negative 30 joule divided by positive 12 volts is equals to negative 30 volts is also joule per coulomb. So the answer would be negative 2.50 coulombs. So the number of electrons is the total charge divided by the charge per electron. That is, number of electrons is equals to negative 2.50 coulombs divided by negative 1.60 times 10 raised to negative 19 coulombs um, per E is equals to 1.56 times 10 raised to 19 electrons. So the electrons pass through is equals to 1.56 times 10 raised to 19 electrons. Problem set 7. Example 9.5. Current density, resistance, and electrical field for a current. Carrying wire. Carrying wire. Calculate the current density, resistance, and electrical field of a 5-meter length of copper wire with a diameter of 2.053 millimeter, 12 gauge, carrying a current of 10 milliampere. So in this problem, the given are: first, the length of the wire, which is 5 meters, the current is 10 milliampere, and the resistivity of the copper, which is 1.68 times 10 raised to negative 8 ohm times meter. So in this problem, we're going to find the current density, the resistance, and the electrical field. So we can calculate the current density by first finding the cross-sectional area of the wire, which is area is equals to 3.31 millimeter squared. And the definition of the current density is um, current density is equals to the current divided by the area. So the current is equals to 10 times 10 raised to negative 3 amperes divided by the area, which is 3.31 times 10 raised to negative 6 meter squared, is equals to 3.02 times 10 raised to 3 ampere per meter squared. And for the resistance can be found using the length of the wire, which is 5 meters, and the area and the resistivity of the copper, which is 1.68 times 10 raised to negative 8 ohm times meter, where resistance is equals to the resistivity times the length divided by the area. So 1.68 times 10 raised to negative 8 ohm times meter times 5 meter divided by 3.31 times 10 raised to negative 6 meter squared is equals to 0.025 ohm. And finally, we can find the electric field. So the resistivity and the current density can be used to find the electric field. So 1.68 times 10 raised to negative 8 ohm times meter times um, the current density, which is 3.02 times 10 raised to 3 ampere per meter squared, is equals to 5.07 times 10 raised to negative 5 volts per meter.